Well, our next speaker, very dear to my heart, is Yago Li. Yago received his BSc from the Wuhan College of Geology in 1983 and a PhD from UBC in 92. And he's currently a professor in the Department of Geophysics at the Colorado School of Mines, and he directs the Center for Gravity, Electrical, and Magnetic Studies, CGEM, and leads that group. And Yago has had a career in looking at potential fields, DC resistivity, and IP, and has done really a lot of the pioneering work in the inversion of a lot of these data sets. He's a fellow of AGU, ASCG, EAG, and he's here to talk to us about magnetics inversion. Yago?
Thank you, Doug, for the very gracious introduction. I realized, okay, so how do I advance this? I was going to say I realized I'm actually the only guy between you and the coffee. So I'll make it fast, and but no tomatoes if you run over time. So the talk title is, as I mentioned, the advances in the 3D inversion magnetic data in the presence of strong remnant magnetization. And there's a lot of things has happened over the last decade. So I'll try to go through and take myself out of the context, kind of give a review of what advances have been made by the community at large. But before I start, I would like to thank Peter Folligan and Doug Unberg for the invitation to present here. As Doug mentioned, this is a topic that's close to my heart. But also, I want to mention Tony Watts and Jules Leroy. So years ago, about 15 years ago, Tony actually, after we finished the Mag 3D inversion at UBC, Tony showed me this map, says, Yago, you invert that. And it was actually a challenge. That data set has remained to be inverted because I don't have digital data. But that actually challenge actually made a really set the tone for what I've done. And also, George Leroy actually provided a set of data from Victoria Island that actually guided our research. And that also cast interesting light for us to look at, for me to look at the work that's done within the community. So over the years, I've worked with many students and colleagues on this problem. So that's probably, there's the reasons why I'm standing here talking, giving this review. Of course, a lot of research we've done over the years is supported by GMRC. With that, just a quick image. It's a challenge. This data set George Leroy provided from Victoria Island in Northwest Territory. One look at this, given the inducement field is vertically down, you have multiple anomalies that's in all sorts of different orientations. That's actually turned out to be a typical scenario in the magnetic data set. Look at any data set, you can see this kind of features, but these are distinct. So that's really the perennial challenge that the community has been trying to figure out. The difficulty in this particular problem, doesn't matter how you do the modeling, integral equation, differential equation, or any other approach by parametric modeling. The issue is really highlighted in the first equation. The detail is not important. The important part is the J and the J hat. Those put together is the magnetization vector J. And in the case of wake-induced magnetization, then J hat is the B naught, the inducement field direction. That's what actually we've been operating for a long time. But as soon as the 3D mag inversion became widely available, then you realize there's so many more data sets that cannot be handled with that. One of the primary reasons you have the sum of the induced and the remnant component. Therefore, in this case, the J hat, the direction becomes unknown. That's one quantity we relied on so much on in the past. Now it becomes unknown. Therefore, looking back in the last 10 years, majority of work actually revolves around how to deal with this issue. So if I try to put together a good summary of that, actually we can walk away and for the practitioners and researchers alike, have a good sense of overview of what actually happened and what tools available. This is best I came up with. So you have three major categories. First, parametric inversion. Second, mixed parameter inversion, which involves geometry and the physical property. The third category, by far, is the most popular, most active area. That's generalized inversion. You're looking for a 3D model. You're approximating the function. Then this area, there are just three subcategories. I will try to go through this one by one. So let's start with parametric inversion. This is perhaps one of the oldest inversion approach in the geophysics community. As soon as the generalized inversion became available, this kind of fell out of favor until it became a prominent method in the remnant magnetization issue. One of the types of work that Clive Foss and Mackenzie did, actually, Clive gave a fantastic talk this morning, is using this type of model. And one of the key advances is instead of a single parametric model, they put together the assemblage of these models, so that allows us to handle very complex anomaly and associated structure. So this is one of the example from that 2011 paper. They have much better result, but this is one of their first result. It's striking in terms that you use simple geometry model, you can actually come up with the very complex modeling. So that's the parametric. The move on, next one is the mixed parameter inversion. We're looking for geometry and the physical property. So in this case, the unique work done by Peter sitting here, and Galen earlier spoke on the similar subject. Basically, you have assemblage of vertical prism with movable top and base. So you have partial recovery of the boundary, whereas the horizontal division is fixed. Then you look for the magnetization and the susceptibility, other properties. So in this particular concept, the context, the third panel on your right would be the one that's actually we're dealing with. So this is an example that shows a synthetic simulation based on a realistic scenario where top perspective views data, bottom basically have a intrusive plug that has strong remnant magnetization embedded in the magnetic background, primarily susceptible, so induced magnetization. In this case, using this algorithm, you can actually recover the smooth varying background susceptibility and a very distinct intrusive plug with the very different magnetization direction. So this is actually with hybrid in many different ways, sets between the pure parametric and the generalized inversion. Now move on to the category 3. As I mentioned, this is by far where the most activities happened. Under this category, there are 3 subcategories. It's actually interesting. Look at all this. They follow a very nice research pattern. First is that you don't know the magnetization direction. Therefore, let's estimate if you can. So this is estimation direction. Second is that you cannot actually, do not know the direction. So let's actually get around it. Typical approach again. So that's where you transform the total field anomaly into a quantity that's insensitive or weakly dependent on magnetization direction. Then you go ahead, do the inversion, find the magnitude of magnetization. That basically puts you on the equal footing with the susceptibility inversion. And there are 2 noticeable algorithms. We'll go ahead with that. The third one, this is really by far the dominant amount of activity that happened and also commercially available. That's magnetization inversion. You're looking for the magnetization, which includes the magnitude and the direction. Therefore, it's a vector. So there are 6 algorithms in this category. We'll try to go through one by one. So first one, that's the direction estimation. This actually is perhaps the most familiar with to most of you. This actually work there's, if you go through the complete list of literature, there has to be several dozen. Would be not surprised if you get a couple hundred of these from different communities, including the environmental application, mineral exploration, petroleum application, and solid earth geophysics, a lot of work. So the idea is actually, this is partial list of the references, but you have isolated compact anomaly. That's where you can best estimate magnetization direction. Then you put that into any existing susceptibility inversion code by specifying the magnetization direction as the one that's being estimated. Then you go ahead to the inversion, end up with the magnitude magnetization. Often it's presented as effective susceptibility. So this is an example from Victoria Island, simple in kimberlite dike. Vertical inducing field down, but the central part is reversing magnetized. Now, in this case, it's ideal. You can do the estimation number method, where they all perform quite well. You go ahead, do the basically inversions. This is what's done with Max 3D from UBC. And you notice you recover very nice compact anomaly, depth and the trend and the structure. That's what you're looking for. But the problem is this actually has limitations. It cannot go beyond a simple compact anomaly. So that's when the next group comes in. That's the transforming of the total field anomaly into a direction insensitive quantity. There are two large categories. So as I mentioned, the approach is that basically we do not know the direction, so let's actually go run it. So in this case, then the two types of data actually emerged. One is amplitude data associated with that. Often people have done the total gradient data. But the nice thing about amplitude data is it's actually same dimension as total field anomaly. It also preserves long wavelength signal, which is really good for the exploration applications. The second part is normalized source strings, which turned out, based on Mark Pelkin's work, is actually least dependent on the direction. Both methods involves certain approximation because it's not totally independent. So let's go through that. Conceptually, the first one is you need a three component of the anomaly. You sum the square root. That's the length or amplitude of the anomaly. There's a whole long history of the use of this. In fact, I can trace earliest back into a paper in China in 1979. And so there's work done in this. And so this example is done by Marcelo Santos. And example is from the Furnas South IOCG deposit. The image on the top left is total field anomaly. Note here the inducing field has inclination of -5 degrees roughly. And yet the anomaly looks like it's somewhere from induced anomaly in Colorado or Ontario. So clearly it has strong remnant magnetization. But if you transform that data into the amplitude data, then that's the image shown at the lower bottom. Notice the peak of the amplitude data lines up with the dark line. That is surface projection of the deposit. That's where that's the source of the anomaly. Now you go ahead and do the nonlinear inversion of the data. You end up with a model shown on the right. The reddish color is the inverted effective susceptibility with only positivity constraints, and the green body is actually, they have hundreds of drill holes. That's the susceptibility model constructed from drill hole logs. So these two are highly consistent. That gives credence to the amplitude inversion. Then move on to the normalized source strengths. This is really neat results. Earlier work of this done is in Canada actually, for the target detection using the magnetic gradiometry. And basically you take the magnetic gradient tensor, you do eigenvalue decomposition. You can define the invariant quantity, which is shown as ns as the square root of the -2nd eigenvalue squared minus the product, the first and third one. So this actually, Mark Pelkin and Majed Becky developed algorithm. The result is shown here. So the top, again, top left is the total field anomaly. And clearly, this is again in Northern Canada. You have a strong remnant magnetization clearly showing up. You convert that into the NSS. That's the lower left image. Again, very compact, well-defined anomaly. You do the inversion of that against nonlinear inversion. You end up with the model shown on the right hand of the screen. So that concludes the direction insensitive data. Then we have moving to the generalized inversion, which actually has 6 subcategories, 6 distinct methods I was able to find in the literature. And so in this case, we're back to the total field anomaly. But no matter how you parameterize it, you're dealing with 3 3D models. For example, what's shown on the screen is the 3 vectors dealing with the 3 components of the magnetization vector. There are other parameterizations, but you cannot actually reduce from this set. So the challenge is really, for most of what we do, we're dealing with surface data. It's a 2D entity. And at most, we might get some data from sparse boreholes. But so that's a 2D entity. But the unknowns we're trying to recover, it's really challenging. 3 3D functions. So in the magnetics, we have a 2D entity, 2D data set trying to recover a 3D function. That's already challenging enough. We recognize we need information to supplement what's in the magnetic data. But in this case, the problem is basically triply bad as compared to susceptibility inversion. So the key is that we require additional information. Any effective algorithm need to inject information into the inversion in some way. May it be explicit information or implicit or site-dependent or general type. So all algorithms, if you want to actually look at, understand it, try to find the correct one to use for your problem, that's where I would recommend you look what type of prior information constraints is required in a particular algorithm. So I listed 6 here. We'll go through that. First, I would say this is seminal work that Peter Lilia did with Doug Weback, part of Peter's thesis, and published later on. This really is the first work that showed that you can actually, despite the challenge of trying to recover 3D functions from a 2D function, you can do it. All you need is the correct appropriate type of information. So in this case, what Peter did is actually parameterize the magnetization in the inducing field reference frame. You have one direction dominant in the inducing field direction. The parameter has 2 orthogonal components. Those 2 orthogonal components must be Rem magnetization. So that actually has really nice separation of the different parts. Then you form an objective function with a particular weighting factor gamma, in this case, that actually limits how much of the remnant components you would allow. What that does is that you can now determine that limitation based on any type of realistic prior information, may it be geology, petrophysical, or conceptual understanding, or Q ratio you can have. You can determine this limitation. That's actually really fantastic. So this result showing again similar type of data set. You have a strong remnant magnetization. You go ahead and do this inversion. So what Peter, 5 minutes, okay, cool. So that's, I think I can make it. So let me actually go back. So the other one, so one mentions later on that becomes relevant is Peter actually showed in the direction from top and bottom is actually quite a bit different. I'll come back to that later. So later on, the next is the now commercially available package is compactness and focusing objective function that shows Bob Ellis and others have done. So on the left is kind of just illustration purpose in their publication. You do a susceptibility inversion without any constraint, although that's not commonly done, but that showcases what challenge is. In that case, you have 2 distinct bodies with different susceptibility, one positive, one negative. On the right is the consistent magnetization direction you can recover from this. Third one is really neat. A cooperative approach, you do the amplitude type of inversion, recover the magnitude, then you follow on by the second stage, trying to determine the magnetization direction. What's neat is this group, Liu et al. From Chinese University of Geosciences did was they applied this to drill hole data, multi-component. You have multiple components, you can calculate the amplitude data directly. Then you do the 2-stage process. On the left is a synthetic example. On the right is a result applied to a real case that actually from the magnetite deposit, highly remnant magnetization. So the fourth one is a Gramian constraint by Zhu and others, basically the Steinhoff's group. So they've been using this for joint inversion quite a bit, but the deep down, if you look at the Gramian, which is basically determinant of 2x2 matrix made of the inner product of 2 model vectors. You simplify this, that comes back to something proportional to the sine theta squared, where the theta is the angle between the 2 vectors. So you're really looking for each component of the magnetization to be aligned in terms of the algebraic vector with the magnitude. So this result on top is their true model. In the middle, that's the unconstrained inversion, not very meaningful. You put the Gramian constraints, you find a coherent structure. So fifth one, this is actually done by Dominic Fournier and Doug's PhD student. I think he's still finishing that. This is by far the most comprehensive collection of single body of work on the remnant magnetization. So they use a structurally oriented object function by doing local rotation of coordinate system. Then use a mixed norm. Specifically, smallest model is L0, and for the structure L1 or L2, shown on the screen as one example. Then they developed a scaled iteratively weighted least squares to solve this problem. Makes it a lot more stable and efficient. And this is one of their fantastic results. I just couldn't actually get over this result. So cool. So construct this model, you have acute shaped anomaly and a middle, another one in the middle. On the right is the synthetic simulation. You notice in the arc-shaped source, the magnetization direction is changing all over the place. You consider this almost as a result of structural movement or deformation. This actually has huge implications. Then you do this approach, the result on the right is recovering this, both the geometric extent and magnetization direction really nicely. And I'll try to come back to this a little bit towards the end. So the last one of the last category, so that's fuzzy-Simmons clustering. So idea is you discretize the model into a large number of cells. That's purely for the numerical flexibility and parameterization. But geology has a small set of directions, a dominant coherent. So this behavior is actually described by fuzzy-Simmons clustering. So the illustrations, the image on the lower left is the scatter plot of the magnetization direction without any constraints. Now what you do is actually use the classification approach. You ask the directions to be coherent within a subgroup contiguously towards a certain direction. Then you can pick the direction, number of direction groups, you end up with the type of inversion in terms of plot of direction on the right. So very coherent, that carries information. So this example from, again, the data set that from Victoria Island, simple data enough, you have the negative anomaly in the middle, bunch of small anomalies on the outside. And in this case, you can start thinking, okay, how many directions I might expect? First of all, you just see the anomaly in the middle. It's reverse magnetized, but you don't know what direction. That's one direction. The positive anomaly on the outside is one group. But then you got allowed induced magnetization. So you assume 3 as one starting point. The result shown on the right in the polar plot is 3 distinct directions that turned out to be highly consistent with known geology. Look at the model, you have coherent directions. So a quick summary. So this is really what I think is the state of the art in terms of inversion in presence of random magnetization. That same chart I showed. But put this in context of state art of magnetic inversion in general. So we can actually do the 3 scenarios. Weak-induced magnetization, and we just discussed a whole bunch of method in the case with remnant magnetization. Then the soft magnetization, their whole body of work that's existing, and we did not touch on that. But what I want to mention is a lot of methods that's developed in not everyone, but a lot of them developed in the remnant magnetization inversion can be applied in the soft mag case. So quick look ahead. So what does this mean? I think really take a step back. The understanding, I think, we can walk away, at least from my standpoint, is the magnetization magnitude of susceptibility gives you the source configuration, spatial geometry, and magnetite content. The magnetization direction actually encodes information about the formation process and the structural movement of the sources. That actually then leads us to 2 distinct possibilities. One, we can use this to do geology differentiation, distinguish different magnetic sources. But more importantly, I think now we have a collection of tools to invert magnetic data. Then the question is, how do we actually now using these tools, instead of focusing on tools itself, but actually using these tools to integrate with other geophysical data. So this example for geologic differentiation, I will not go into this, it's in the paper, and I will leave there. Thank you.
Thank you, Yago. I think there's time for a question or two. Anybody?
Cool. Get off easy, no question.
they're going for lunch or for coffee. Okay, listen, thank you for all of the speakers and for all of the attendees who came. I think you all deserve a round of applause.